Hey guys, we're in my bathroom because I don't have a whiteboard big enough to show you anything cool. So we're in my shower. Welcome to my shower. Now I want to talk about the things we just did outside, dropping the Coke cans and dropping the pieces of paper. And I want to look at those through what we call free body diagrams. That's free body diagrams, right? So if you remember from the first semester, you draw a free body diagram by simply just making a square to represent anything that has forces acting on it, right? Like a Coke can or a bullet that's dropped from my hand or fired from a gun or a basketball or an airplane, whatever it is, you can just draw a square. So I'm going to draw a square to represent each of the Coke cans that we dropped. Now, of course, one Coke can was full of Coke, right? And the other was empty. So we know that one has more mass than the other. You put the mass inside the box of the free body diagram. So let's say the one that had Coke in it was 5 kilograms and the one that was empty was 1. Now, an empty Coke can is not 1 kilogram and a full one is not 5 kilograms. I'm just doing this to make it easy because what's really important here are the forces that are acting on it, and we diagram those using arrows, right, showing the magnitude of the forces. So when we drop those Coke cans, you are right to say that gravity acts on both of them, right? So I'm going to draw that using an arrow, right? And I can label that F sub G for force due to gravity, right? And we can see that these forces are the same, right? So this force right here is due to the mass of the Earth, right? And the mass of the Coke can. But you can see that the Earth cares just about, it cares the same about the full Coke can as it does about the empty one, right? So they're exactly the same, right? They fall at the same rate of speed. And that is, if you remember, the acceleration due to gravity, which is 9.8 meters per second every single second, or 9.8 meters per second squared. So are there any other forces acting on this? Well, yes, there are. So if you drop anything, the air is going to push back up, right? And that's called friction or air resistance, right? The friction due to air. So we can call this air resistance or the force due to friction if we want. And it's very, very small on things like the Coke can or like falling pennies or a basketball. Very, very small, right? It kind of just cuts through the air. But some things are not like that. Some things that have a big surface area, which is what we did with the papers. So let's do another set of free body diagrams with the 2 sets of papers. So those were the same exact mass. Let's say it's 1. And, of course, gravity is acting on it, the force due to gravity. Now, what about the frictional force? I crumbled one paper. It had a very small frictional force, almost like the Coke can, right? And this one, you saw it blew away, kind of acted like a parachute. There was a very, very large frictional force on it, right? So I drew this arrow bigger. So the force due to gravity is still going to win over the frictional force, but because the frictional force of this one is so much greater, right? Those two forces are competing, right? So which force actually wins? Gravity actually wins, but it brings it to the ground much more slowly, right? So you're right to say that some objects fall to the ground slower than others, but it's not due to their masses. It's due to the forces that are acting on them, right? So if you can understand that, understanding the next part is key. What if we start diagramming the bullet that is, I'm going to erase this, but everyone knows that the acceleration due to gravity on Earth is 9.8 meters per second every second, 9.8 meters per second squared. Now, let's start diagramming the bullets, right? The bullet in my hand and the bullet in the gun. So you should see that those are the same mass, right? So let's say it's 1. A bullet is not 1 kilogram, right? But this is just going to make it easy. It's the exact same. Now, of course, there's when I drop it and I fire it, when you fire a bullet from a gun like this, it's going to go, but it's eventually going to hit the ground, right? Why? Because gravity's pulling it down, right? And if I drop one from my hand, it's also going to experience the force due to gravity And we know from the Coke can experiment, the force due to gravity is going to be the same. It's going to accelerate it down at 9.8 meters per second, no matter what, irrespective of the mass. But these have the same mass. Now, is there air resistance in this direction? Yeah, just like the Coke cans had, but it's very, very small. Very, very small. So we'll call that force of friction. And it's going to be the same on both. They're both the same shape, the same mass. The force of friction is going to act on them the same. Now, are these the only forces acting on both of these bullets? The one that's dropped and the one that's fired. Now, you might say that the bullet that is fired, here's the bullet that's fired and here's the bullet that is dropped, has another force acting on it. Of course, the force that's pushing it forward or pulling it forward. But that is completely wrong. It's completely wrong. These two, right, are simulating the exact instance where this is dropped out of my hand and this is fired out of the gun. After those two things happen, this is what we're looking at. The drop bullet experiencing the gravity and the fired bullet experiencing the gravity. Does the fired bullet experience a force in this direction if I shoot it this way? Does it? What is a force? A push or a pull, right? Let's look at this in another way. So I'm going to erase this and I'm going to draw a graph, right? I'm going to draw a graph that, just like any graph, has an x and a y component. Now let x be horizontal, so like the ground, right? I can walk horizontally, and let y be vertical, up and down, right? So ask yourself, how does gravity work? Which direction does it work in? The y direction, up and down, right? And x, of course, would be like if I threw something or fired a gun, it would move vertically, right? In the x direction. So let's look at this bullet that is fired, right? After it is fired, let's say it's fired here. This is time, let's say at time 0, it's fired. And now here, at this point, it's moving along the ground and it's going to fall, right? It's going to fall. Eventually it's going to fall, right? Let's look at the velocities here. Let's look at them, right? If I shot the bullet from here, it's going to experience gravity. Well, what is the velocity? So we're going to be looking at velocity here. What is the velocity going down? Well, we just saw, and you should already know, that it's 9.8. The velocity here is 9.8 meters per second every single second. So in the first second, it's 9.8. In the second second, it's 18.6, and so on and so forth, right? It increases its velocity going down, right? Now, let's look at the velocity here. Well, I don't know the velocity of the bullet right now. I really don't know. It's probably thousands of feet per second. Let's just say it's 100, okay? It's not, but let's say it is. 100, sounds like a lot. 100 meters per second. Now, this one is getting faster as we drop it. Is this bullet ever going to get faster? Is it ever going to go from 100 to 105 or 102 or 110? You should know that it won't. Why? The answer to that will tell you almost everything you need to know about this challenge. This bullet will never get faster than in the x direction, but it will always get faster in the y direction. Why? And the answer becomes clear. No matter that the bullet is fired, there's only one force acting on it after it leaves the gun, and that force is gravity. A force is a push or a pull. That is the thing that is going to accelerate something. So you can see it's accelerating in the y direction, aka it's going to fall faster and faster and faster, but it is never going to accelerate in the x direction because there's no force acting on it. It's not a rocket. It doesn't have a little rocket propelling it. It's already been fired, right? It's never going to be faster, right? So if we break this down into x and y, it becomes really, really clear about what's going to happen here. Now, let's put this on a graph X and Y of the dropped bullet, right? So this bullet, instead of being fired, is going to be dropped. So it's going to have no X velocity. Now, what is the velocity here? Well, it's going to be the exact same as this one. And everything on Earth, it's going to fall at 9.8 meters per second squared. So you can imagine this bullet and this bullet right here are going to drop at the very same time. This bullet, however, is going to also travel in the X direction. But which one hits the ground first? So keep pondering this, keep thinking about this. I'm going to show you a small experiment that puts this to the test, and we're going to see what you think about it. So meet me in activity 4, I think it is, and I'll see you on Zoom.